Okay, our next graph is a strong polyprotic acid. Now guys, the only strong polyprotic acid is sulfuric acid. So let's say we were titrating sulfuric acid with our sodium hydroxide. This should look a lot like graph 1. I've got a strong acid in the beaker. The difference here is our stoichiometry. If you look, you have a 1:2 ratio between your sulfuric acid and your sodium hydroxide. You need twice as much sodium hydroxide because you have 2 hydrogens for every 1 molecule of your sulfuric acid. So let's say I told you we're going to use the exact same numbers that we have for the last couple of examples. So say I have 20 milliliters. I have 0.1 molar of this. That's going to give me 0.002 moles of my sulfuric acid. And you can work this one of 2 ways. We can go from sulfuric acid to sodium hydroxide, H2SO4, for every 2 moles of NaOH. So this one is going to require twice as much sodium hydroxide as that first graph. And then if I told you that your concentration is 0.1 molar for your sodium hydroxide, when you do the math, you're going to get 40 milliliters of NaOH required to reach the endpoint, the equivalence point for this titration, okay? If instead you prefer to work it as a net ionic reaction, then we're just going to back up and we're going to convert H2SO4 to just hydrogen ions. So right here, this will be there are 2 moles of hydrogen ions. And then for every 1 mole of hydrogen ion, you have 1 mole of hydroxide ions, because my net ionic equation is still hydrogen plus hydroxide yields water, right? Either way, you're going to end up with a volume of NaOH as 40, required to reach the endpoint. Okay, if we graph this one, pH versus milliliters of NaOH added, we have a strong acid in the beaker, so my pH is going to start very low. It's going to stay flat. And this one, I am extending the line a little bit further than I did. Graph 1, if you remember, looked more like this. Why am I making it go further? And those two should end at the exact same point. So more like that. There we go. So why am I making this one go further? Well, for the first graph we did, it required 20 milliliters to reach the equivalence point. But for this graph, it requires 40. Okay? All right. The theory behind this, though, is going to be identical to that in graph 1. In part A, because I have a strong acid, the hydrogen ions dissociate. So before any titration begins, the pH starts very low because I've got a lot of hydrogen ions present. As I titrate, as the titration starts, I'm going to write, I'm going to draw in here, adding my hydroxide ions in. The hydroxide and hydrogen would bond to form water, but I still have leftover, unreacted, strong acid, so my pH remains very low. This one is not a buffer. I don't have any weak acid and conjugate base present in the beaker, so not buffered at all. Okay, when I get to C, that's going to represent my equivalence point, my end point. I drew in 2 hydrogens, so I'm going to add 2 hydroxides. So if you look at your net ionic equation, the only thing present at the equivalence point or the end point is water, and therefore my pH should be 7. Okay? And then once again, the volume of NaOH needed to titrate the acid will be twice that of the acid, because of that 1:2 ratio. When I overshoot my end point, so I had the water present at the equivalence point, and now I add too much hydroxide. So now I have leftover strong base. So my final pH is going to be extremely high because After I overshoot the endpoint, I now have a basic solution. Okay, and it is a strong base. So this is just like graph one. I start with a very strong acid. I still have a strong acid until I reach the equivalence point, at which time I only have water. And if I go any further than the equivalence point, I now have excess leftover unreacted hydroxide ions, and so it is now a very strong base solution. Okay, so let's go back to the graph. Once again, your graph should look something like this, fairly flat. Okay, for this one, your equivalence point occurs right about here. Remember, I'm looking at where the lines kind of flatten and trying to divide that by 2. It looks like that is right in half. Right half the distance between those two lines is where you draw that dot. Okay? So, ladies and gentlemen, that equivalence point occurs, I'm going to label that equivalence point, that occurs in this case at 40 milliliters. And the pH at that equivalence point should be equal to 7, because the only thing present at that equivalence point is water. Okay, so this dot represents A from your notes. The only thing present is hydrogen ions. This represents B. The only thing present is your leftover hydrogen ions and the water that you're creating. At your equivalence point, that represents C. You just have water. And then past your equivalence point, it's really anywhere past the equivalence point. So you could label any place to the right of C. I'm just going to put it right there. That's D. There I have your hydroxide ions and, of course, the water that was present. So if I was choosing an indicator for this titration, I would need an indicator that changes at a pH of 7. So once again, I'm looking at one of these right through here. I should see a color change right at 7.